Good almost afternoon. I'm Jerry King, and I'm glad to have at least a small audience for this talk. I think you'll find it interesting if you bear with me to the very end. It sounds a little bit intimidating, the title, solubility, and kinetic aspects of 3 or 4 major areas I think of concern to attendees here. And so I'll get on with this. I have another talk to give about another hour and a half. So primarily, I come from the areas of physical analytical chemistry, particularly my doctorate is in analytical chemistry. And I did a lot of work in chromatography, which I think some of you are familiar with. But what's concerned me about sort of the cannabis and hemp areas is the lack of really understanding with physical chemistry what's going on. And I also served as a chemical engineering professor at the University of Arkansas. And that is a group like mechanical engineers that build equipment that have not really had that much entree in this field. So I'm going to basically evoke a certain theory and try and spare you and then taking this same kind of theoretical basis, apply it to the selection of packaging materials for what's called solute. Solutes, you say, are terpenes or cannabinoids. You're trying to infuse into the matrix, and it's usually a product of their solubility. Sometimes you don't really have a knowledge of them, just empiricism. And their diffusion, which relates to the kinetics, how long time it takes to dissolve them, and also to maintain their stability in the matrix. And then finally, I will talk about the formulation of products and issues of miscibility or immiscibility. I think you'll find experience in what's known as supercritical extraction, which is primarily done with carbon dioxide. Sometimes it's liquefied or some critical state, and then also in the supercritical state. I'm not going to get into a lot of the theory of that. That's a whole short course over a couple of days maybe. But primarily to try to give you the take-home messages here. And this is some solubility data on pure compounds, CBD, CBN, THC. It was done in the Netherlands and Holland, which is certainly a cannabis-friendly nation. And it simply shows as a function of temperature and pressure here for CBD, CBN, and THC. You can see there are differences in the graph as you apply different pressures of CO2, different temperatures, and what comes out. Now, keep in mind, these are pure cannabinoids. They are not in an actual matrix, and that changes the game a bit, let's say, because usually you have co-extractors that are coming in with CO2 or ethanol or whatever technique you're using. But I present this with probably the take-home message is that CO2 can be very effective. It's a wonderful technique because it appears very blatantly on various commercial products. It's consumer-friendly, environmentally friendly, and it doesn't leave any solid residues that would be of concern. But to apply it, you really have to use what information you have as well as empirical findings and precisely focus in on studies of pressure and temperature if you're ever to have repeatability in creating a product with this technique. And essentially that's what I'm saying has to be done precisely. So here we get in to this sort of menu, and I'm going to use what's called HSP, which stands for Hildebrand Solubility Parameter. This has been around since 1925, and before you just solvent extraction and that type of thing, but also it can be employed, as I hope to convince you, in the design of systems formulation, There's a classic book here called Hansen Solubility Parameters, and this is a little more sophisticated, and they also offer a program you can purchase. And I think this, if you're in formulation and wanting to study any of these subjects, is an invaluable approach. But what you're looking at in kilogram solubility parameters is what's called the cohesive energy density of a molecule. And all these molecules, be they even CO2 or CBD or say a terpene like beta-caryophyllene, all of them have defined solubility parameters which are the square root of what's called their cohesive energy density, or delta E over delta B. So in 1952, a student in paint and coatings technology, which I'll relate to later on, developed a three-dimensional. And I won't get into that. I'm going to say it more rationalized from a structure of the molecule, how, in essence, the cohesive energy density could be determined, particularly from dissecting a molecule and looking at the groups and hydroxyl group, methylene group. This middle equation that says sigma fluid is one developed by a mentor I had a long time ago. What it has is a comparison of two values called the reduced density of the fluid or the reduced density of the liquid. And basically, when these two become unity or equivalent, the solubility of the fluid is equal to a liquid. Gases like butane, butane oil, for example, or CO2. But the main thing is that when this fluid solubility parameter, solvent solubility parameter, equals that of the solute, cannabinoid, terpene, whatever you're trying to extract, like dissolves hot. If there's a seminal thought you want to take away from this is if we can get them to match things that you are looking up to. It does not mean that you cannot dissolve some amount of it, as you saw with the CO2 solubility data for certain cannabinoids. But the optimal is when the two sigma values are alike. This is a more sophisticated form. I'll show another graph of this later on in terms of why things don't dissolve in glycerol like CBD. But this is a more sophisticated thing, and what it is it defines, as you see, there's a lot of square terms in it. An ovoid, or ideally a sphere, and the center of the sphere is essentially terpene. So the distance, RED, from this RO value defines what's called RED. The RED, again, can be figured out. There are programs that allow you to do this. And when it's unity, you start to encounter miscibility or solubility. If it is greater than unity, you're in an immiscible region. And it's a no-go as far as applying, the systems you're studying here for formulation or extraction. And I'll kind of leave it at that in terms of time, but I think a pictorially slide that will come up later will give you an idea of this. So all these fluids have solubility parameters. You're locked in when you use ethanol as an extraction solvent other than applying temperature. And I'll show you an example of applying that in wax, de-wax operations. With something like CO2, to a lesser extent butane, the solubility parameter and how it acts as a solvent is again defined by the pressure and temperature. And it looks kind of like an asymptotic sigmoid is how I would describe it. Early on, there's an increase in the solubility of these target compounds you want, like CBD and THC. And then it starts to drop off, and you really have to pay a price of applied pressure to get a higher solubility parameter for the CO2. What we have done over quite a period of time for many different solvent systems, including water in compression, is we've defined tables of these solubility parameters. And we also have developed an Excel program that if you literally gave me the structure of any molecule, any polymer, any simpler molecule, we can calculate its solubility parameter. So you see them listed here: hydrocarbons, liquids, critical states for CO2, which are functions of pressure and temperature, liquid ethanol, function of temperature, and so on. And some of these are sort of semi-empirically used solvents like glycerol, butter, olive oil. And this table just follows this up with some other solutes, compounds that play into our formulation and representation of the sesquiterpene and terpene class. Anyway, we can get these values, we determine experimentally, won't get much into that, you can also do it by calculation. So these are calculations of the acidified cannabinoids like CBDA and so forth. And there are these three dimensions of dispersion and polar, they're called hydrogen bonding, as you go across horizontally. The important thing are the two colored segments here and there. They represent different units. The top one is in traditional units. The bottom one, which is a factor of about 2, are in megapascal and half powers, which are more in vogue these days. But these latter two values were calculated 2 different ways, and I think you'd agree that they're pretty well. They're less polar, they're less cohesive energy density centers. And so for THC and CBD, again, you see the same kind of agreement between the two computational methods. And likewise here for essentially 10, 12 of the cannabinoids, including beta-peroxide, the signature cannabinoid that is in Kinetic. And we have plotted these on a relative scale, cannabinoids, the terps also included there. A class of solvents, hydrocarbon-like mainly, and then CO2 and higher up ethanol as a function of temperature. And we actually had the privilege of visiting beautiful New Zealand, working with a woman engineer named Teresa Marino, and she did some very high pressure experiments with CO2, whereas you can bring the horizontal line across at that extreme condition where you centigrade 1,000 bar, you match the solubility parameter of THC. The problem with all extraction methods is they extract co-solvents, not co-solvents, but co-solutes like waxes, triglyceride-based oils, and what I always say is dissipated chlorophyll. And these also have relative solubility parameters that touch on these areas of solvency exhibited by CO2, to some extent ethanol too, and the hydrocarbon gas fluids like propane. So we further developed a relative plot, this is called the surface response plot. So the solubility parameter is a function of pressure and temperature. So we can compute for anything you give us, ethanol, butane, this kind of equation, particularly the extraction solvents, they all have very similar resemblance. So we did this for ethanol because ethanol, particularly as you cool it down to subambient temperatures, is used for removing waxes from extraneous co-extracted materials from the enriched CBD and terp area. The take-home message from this slide is you see the solubility parameters on the vertical axis, you see the temperature going colder that way. I think you can read some of the symbols maybe out there in the audience, but basically you see that there's a nice overlap between the terpenes that are listed there and the waxes the waxes and the interfering materials. Actually, ethanol is a very poor solvent for terpenes. And again, this is rationalized by the solubility parameter theory. But it does show that it's very effective at cryogenic or cold temperature in precipitating. So here you're dealing with immiscibility between the ethanol and some of these constituents. And I was privy to supervise an industrial advisor team up at the University of Alberta called Capstone Chemical Engineering Senior Design Teams. And they plotted some of the ethanol-wax solubilities. This is not generally known. And then they used a fitting routine. As you can see, it drops precipitously, as it should. That's why you're using like mop out of the exhibit area. That's what they're doing continuously for their ethanols. They have it at minus 40 degrees centigrade. And you can see the solubility of these materials. The wax compounds really drops out substantially. It has real-world solubilities for 3 different compounds at 25, 20 degrees centigrade. We use this HSP radial spheric method. Not a very good correlation. You can see the R-square value is 0.96. So this gave us some confidence that we could use the solubility parameter theory to estimate solubilities for these as a function of temperature. Now this is another sort of simplistic theoretical concept, but I think it's critical. There's something called the activity coefficient. And activity coefficients, to put it in the simplest terms, is if you don't like the medium you're in, you're going to have a high escaping tendency, or activity coefficient. You're going to want to get the heck out of there, so to speak. So what we have here and we've expressed it in terms of very simple solution thermodynamic theory. And the thermal activity coefficient of the log of it is equal to what you see in the second line here. So this gives you a little bit of a physical reality as how these solubility parameters differ, how they impact on the escaping tendency. Like you'll see in a minute, why would a virtually insoluble cannabinoid like CBD want to spend any time in an aqueous environment, like a citron, a beverage, or water, for example. You'll see an example. So you use nano-emulsification techniques to create a false sense of solubility that in time will precipitate on you as it sits there in the shelf month after month. Anyway, let's see some results from this. So we use for ethanol as a function of temperature. You can see 20, 75, minus 80 centigrade. And also for beta-carotein, which is, as I say, the major, oftentimes, assessment terpenes in hemp and some cannabis strains. And you can see the numbers vary radically. Some of them are exponentially huge, like 3.22 to 10 to the 12. Some of them are very close to unity. The ones that are close to unity essentially force conditions for the terpenes, and also this is true for the hydrocarbon solvents. In fact, it's generally known that protein butane extraction gives the best terpene-rich fraction from the consumer point of view. But there are other conditions, where it's absolutely lousy behavior. So this is how you kind of rationalize what you're seeing in the cannabis field in terms of processing. We're going to apply this to formulation. So here's a quick example of, again, a butane surface response plot, pressure, temperature. Most hydrocarbon fluids are used at 80 to 110 degrees centigrade. We plotted again some of the major interfering constituents, including the propylene as a signature terpene. And we've done it with butane. You can see. So somewhere between 0 and 50 degrees centigrade, if not lower, is where the action of butane or propane is going on. And under these conditions, you've got lines of resecting, very good solubility. However, as you see, again, the Ethanol-Waxes, the interfering compounds, they show no overlap, so they're very miscible. So what this comes down to in real life, you may have heard of essentially diamonds or THCA solving out. You can buy this where it's legal in certain states. And after you start to devolatilize the material you extract, you get this terpene-rich sauce. And then you also have a THCA phase, which is what empirically are called diamonds in this case. And this is a result of diamonds. These have been using activated carbon. They've been decolorized on the left. This is still contaminant material. But again, the difference in the two solubility parameters from the butane and the extraction condition of the THCA, eventually as that butane comes out, you get this precipitation because they're no longer matching solubility parameters. However, it's also kinetically dependent. You have to let these things solve out, precipitate out as a function of time. So the immiscibility you desire to get your crystalline THCA is both composition and time dependent. When I say composition dependent, the other things you're extracting with it are influencing the solubility of the diamonds. This is interesting. I put this in here at the last minute because I was talking with a gentleman who, one of the blues said that they use CO2 extraction because the ethanol extracts which they tried tend to be contaminated with pesticide residues, and they tend to be also have heavy metals more. And this makes sense because if you look at this, the solubility parameter on this scale for ethanol is about 25. So it's very, very close in a lot of these surveyed pesticide residues, including microbutanol, which is used somewhat universally in cannabis in the United States. So again, it rationalizes the extraction and appearance of contaminants. With CO2, the solubility parameters are much lower, a little bit more soft scale. So it doesn't usually yield an extract that is enriched in even ppm levels of pesticides. So let's switch sort of gears here and talk about the product formulation and choice of food packaging materials. So as we attempt to do, particularly with concentrates, a whole bunch of food matrices that range from fat-loving or lipophilic, vegetable oils, medium-chain triglycerides, chocolates, essential oils. Then we go into these more polar matrices, like the gummy bears, carbohydrate-rich, have many other constituents in them, but they're polar. And of course, the most obvious contrast to the vegetable oils is the high water content. CBD has been infused, all sorts of things, coffee, tea, beer. We have some examples out in the expo. And then there are also polymeric agencies of chewing gum and starches. So this is just to bring this point home. When you're infusing CBD and coconut oil, although it will have an upper solubility limit, you have a much more generous latitude to miscibilize and to have it homogeneous. I'm going to drive that point home in a minute. When you get to water, if you just put it in there without any kind of nano-emulsification or the adding of adjunct chemicals such as phospholipids to induce solubility, you wouldn't get this clear water aqueous beverage here. You would have cloudiness in this case. And so I think in formulation, this approach to using solubility parameters can help in the design of your formulations. So the role of solubility is it's a differs in time of also packaging required. At one point in my career, I worked on an FDA-related project. By the way, the FDA is waiting out there to weigh in on this. Right now, they're more concerned about truth in labeling and this type of thing. But basically, in the classic regulatory thing, they were concerned about polymeric adjuvants, the oligomers, residual solvents, additives or excipients that were in the polymer thing. This is a PET, polyethylene. So it was what was going into the coat matrix that was of concern. Or in the case we worked on, it was a microwave PET material. They were concerned about the microwaving, bringing unwanted chemicals, toxics into the food material. In the case of cannabis, that is a legitimate packaging, more than likes the matrix you put it in. This is particularly true for these polar vapor cells. This is a kind of a complex slide, the next couple, but the main take-home point of this, and there's a reference here, is that you have this permeation phenomenon, migration of monomers and additives, and also adsorption. And this has got an empirical term called scalping, or flavor scalping. You're losing flavors like essential oil components that enrich the food or the cannabis making. So you have this back and forth equilibrium across the polymer film. And I worked in the polymer industry in several places, like for American Can, Chicago at one point. Became very familiar with coatings and packaging chemistry. Some of these polymer films are very complex. They consist of 5 or 6 different layers. Some of them are simple. And you'll see an example of stability parameters from several of them in just a minute. Here they are. This is the Hildebrand solubility parameter, PET, or the polyolefin, polypropylene, polystyrene. These are basically constituents that appear in unanimously, I would say, in many of the formulations and packaging that are used. And they do scale differently in this case. Obviously, PET is more polar polymer, as is nylon, short for polycarboxylate. Polybutadiene would be simply something like a rubber constituent on a bottle where you're doing oral illustration. In a simple tincture bottle constituent, if you unscrew it, or cannabinoids. It has, of course, the rubber that you squeeze, administer it orally in your tongue. It has a cap of the polymer. Inside the cap contains a liner, this polymeric. And in this particular case, the actual thing was not glass, but it was a polymeric. So the take-home message here is that if you're doing tincture of other constituents, you need to be concerned with the migration of your cannabinoids and your terpenes into these polymeric materials, as shown here. And this differs from the previous slide, 2 slides ago, in that I've included cannabidiol solubility parameter in water. And notice how high water is relative to CBD. We already know you have to go to special precautions to get a kinetically stable emulsion in water. And you can see, obviously, I think the point here is that CBD would prefer to go in PET, basically. Get out of water, which is the case, that I previously spoke about. So CBD's activity coefficient in water at room temperature is of the order of 1.5 times 10 to the 38. That's a huge number. So it says essentially it's immiscible. That bears out its reality. On the other hand, CBD going, favoring, escaping into PET is much more feasible. It only has a value of 2.88. So when people look at label disagreements in our industry here, And they say, well, we put so much CBD or THC into a matrix, such as the aqueous matrix here. We don't get consistency of the values when we do analysis. And this is why. I do ballroom dancing, and I give my instructors these topical patches to alleviate the pains they feel. And this is a cross-section of the topical patch that would have a pharmaceutical, or in this case CBD drug in it. They take on several formats, but they involve a absorbent polymer, and they also involve, skin polymer, so to speak. And actually, filament solubility parameters have been determined for human skin. You can see a range of values here, what's called SIBO kind of solubility parameters. So this is based again on literature reference, which is given there. And this is what one looks like in real life. And if you peel back the protective layer here you have the reservoir well, where you have the CBD or the cannabinoid, maybe with its entourage terpenes, that, depending on what it states, will diffuse out from anywhere from 24 to 96 hours or more days is typical for topical CBD patch. So I wasn't sure that this would apply and was delighted when I found this paper. It's almost 90 current paper, current year, in an Italian pharmaceutical journal. And this 10 or 12 compound constituents, this formulation, all the components are listed there. And we're particularly going to look at CBD and this whole acetyl oxyceramic. So they use the same method we did, called the Fedor's method, to calculate the solubility parameters in this case. And what the interest is how do those solubility parameters of CBD and these compounds compare to the human skin? So I've tried to summarize this in a way here. The implications of this patch test is the CBD permeation rate profile is essentially controlled by regulating the composition of your formulation. The similarity of the CBD and this orthoacetylglucoceramide, or CER for short, their solubility parameters are very similar. So the CER aids the CBD and it's transferring to the skin, in this case, on the stratum is important in that basic work. So essentially, the compound you're trying to medicate through the skin is a function of thermodynamic activity and the kinetics of transfer. There are equations for that. But it can't has been reported in the literature. They're not stated. With the patch approach here, they felt, the authors, that the CBD stability over time was improved using the transdermal patch. I believe that things like molecular, polymer imprinting will be applied in this field. So we're getting close to the end here. I picked up a sample of the vape cartridge solution. It confused me because you, I think, might be able to read there. They wanted you to apply a little amount of heat to the vape cartridge before you lit it up. And if you look at this, the choice of glycerol is a very common adjuvant to use. Propylene glycol is another one, of course, the notorious vitamin E. The choice of glycerol is a pretty poor solvent for, again, dissolving CBD in. So there you can see, I think, a little bit of cloudiness, and this is what has been warmed up to a repair. So what happened here? Well, the CBD solubility parameter is about 24 units here. And glycerol is much, much higher. So basically, CBD has no solubility appreciably in glycerol. Why? And you essentially approximate the solubilities that would happen here. You get what's a mess. We did this for a series of organic compounds and other solutes to define the sphere. Then we took the solubility parameters of the 4 major cannabinoids, you'll see this in a minute, and wanted to see if they were soluble in glycerol or insoluble. And what we discovered is they all had these RSP values were greater than unity, which means they fall outside this solubility parameter sphere. And there are the actual RAD values, so the unity. This again is based on some work. So as I finish up here, we take examples of food matrices again, and how this plays into formulation. It's been known for some time now in analytical chemistry, chocolates, brownies, that kind of matrix, that what is put into the matrix somehow disappears, and it's been a bit of a mystery in terms of scaling the sampling size of the chocolates or whatever the matrix is. Well, one of the problems that people don't appreciate is simple chocolate has different phases in it. It appears physically to be homogeneous, but it really isn't. It has a crystalline phase, and it has a what's called an amorphous phase. Usually the solubility of solutes like CBD, terpenes are more soluble in the amorphous phase. This is just simply some phase diagrams for these triacylglycerols, which are the defining triglycerides in the vegetable oils and butters, materials like that. And there have been studies of the mixing behavior of these components. So this is something to be aware of. It sounds like a lot of trouble, but it's the real world case when you start to try to use infusion methods on these fairly complex matrices. There have been several reports that when you infuse something like cannabinoid into something that even has a weak acid, like citric acid in gummy bears or something like this, that you're losing cannabinoids, or there's a chemical transformation. Catalyzes conversion of cannabinoids in that matrix. So reactivity in the matrix is another consideration. And this is kind of a more blatant example. I walked this and tried to take a hot bath. So here's CBD in a bath ball. They have them out here in the expo. And it has citric acid in it. So the citric acid, even though it's viewed as a typical ingredient in a lot of bath bombs, when you have CBD in there, you're risking, particularly as you store it, the loss of CBD, or chemical transformation. In this case, maybe like CBN. I'm going to talk about that this afternoon. I'm going to talk at lunch. So if you're interested a little bit in this, our time is short. We do have a booth, largely devoted to CO2 extraction. It has assortment of products there. Be glad to talk to you or give you my card afterwards. My contact particulars are there. I have a website. It's of some interest. And I really appreciate you attending. I realize we're part of the lunch hour, but it makes the work I put into this worthwhile. Thank you again. It's been an honor to talk. Hopefully I've gotten some seminal points from us. Thanks again.